so please start.
Okay, so thanks a lot for inviting me. I'm very happy to be virtually in Moscow, even though I would be more happy to be literally there. And by the way, I really like your design. So you probably have a very professional designer because this all looks great. So, you know, unfortunately, I cannot be really in Moscow because we are living now in the day 399 of the new era. I hope this new year will end soon. Okay, so this talk is based on a really freshly published paper, which we wrote together with Masahide Yamaguchi from Tokyo Institute of Technology and our two very nice and brilliant students. Pavel Jirushik is my student and Keiga Shimada is Masahide's student. Okay, there the title was a bit different, so there we were finding constants, and in the talk we are discovering constants, but it's more or less the same thing. So just to keep in mind, if you want to look at this paper, the archive still contains an older version where some of the formulas are not present. It's not a very big step, but nevertheless, so just either download it directly from JCap or look at archive maybe in 2 days. So it will appear like really revised version. Okay. So let me immediately tell you what is my message to take home from this seminar. So there are different points I want to stress, and I think they're pretty unusual and pretty interesting to understand. So first of all, they're local field series. Here by local, I mean that the action functional is actually a local functional on fields.
Action functions local.
So, do you still have echoes, or it's okay? Okay, so there are local field series where the dynamical degrees of freedom are actually global. Okay, for instance, they can be given by integrals over the whole Cauchy hypersurface. So it's already kind of strange situation when we have, let's say, it looks like it is a field theory, but in reality it's almost mechanics. Okay, so there is practically only time dependence there, and this time dependence is trivial. So these degrees of freedom can actually mimic free parameters, or what we usually call fundamental constants. Okay. However,
sorry, are you demonstrating slides or not? Because we don't see anything.
Oh yeah. No, wait. I'm demonstrating now a slide. It's
no, we don't see any.
Do
slide.
you see my?
Or does anyone? I don't see.
Wait, what do you see? Wait
just you. Just you.
We just see you. Maybe that's enough.
No. Wait a second. Good that you told me. Okay. Wait a second. That's okay. Because I started to share, I thought, good that you told me. Okay, let me start from the. Fantastic. Okay, so now do you see my slides?
Yeah, now we see them.
Yes. Perfect. You know, probably what happened is because I connected also through this iPad, and probably somehow I was sharing it there. I don't know, but okay, so sorry about that. Okay, look, that was my first slide, and I abused your graphic designer because that was very nice. So that's this paper which we published. So you can look at credentials and so on. So, and that's message to take home. Okay, let's now go in details. Good that you told me not in the middle of the talk. Okay, first of all, there are local field series where the dynamical degrees of freedom are global and given by integrals over whole Cauchy hypersurface. Then these degrees of freedom can actually mimic free parameters of fundamental constants. And for example, one can model even things like cosmological constant, Newton's constants, and surprisingly even h bar, so the Planck quanta, using such global degrees of freedom. Actually, you know, I was thinking also to maybe do it for the speed of light to close the what is called sometimes Bronstein cube, but it looks like maybe a bit more complicated. So the interesting thing is, as now these constants are not constants, but global degrees of freedom, actually they are necessarily subjects to quantum fluctuations. And that's unavoidable. And that's somehow not very much appreciated in the literature, let's say, on unimodular gravity. And the origin of the values of these global degrees of freedom should be then in quantum cosmology. Because if you want, here we are talking about fluctuation of, let's say, G Newton or lambda or something in the whole universe, because we need whole Cauchy hypersurface. So then it implies that values of these degrees of freedom are actually really somewhere in quantum Big Bang or in quantum cosmology. And if you want, that provides you an ideal landscape, or landscape for poor people, because we don't use any string theory, anything, no real complicated and nice geometrical constructions, just very primitive approach, and nevertheless, we have a continuum of values to choose from. So that's the interesting thing. So I'm not going to solve a cosmological constant problem, but I'm just trying to put there a different point of view on the origin of these constants and maybe on the origin of the problem itself. Okay, so let's now start from more meaty part. So first of all, what a strange theory do we have? Imagine, so formally speaking, our gravity, if you throw away all irrelevant operators, then what we are left with is Einstein-Hilbert action augmented with cosmological constant. Sounds like a nice formula, and it has two-dimensional parameters, two-dimensional, as we would say, coupling constants, and the values are given by these numbers. Okay, it's kind of funny because they have opposite dimensionality and almost the same value. Well, 10 orders of magnitude now, it's not that big deal. So, but if we express it in electron volts, it is what it is. But what is more important is that allows us to create out of them a dimensionless combination. And this is famous problem, which is 10 minus 122. Okay. So this is pretty strange because we have a theory. Formally speaking, we can all write it in, say, Planck units. But having lambda, we could switch from Planck units to, let's say, cosmological units. And still we would have enormous numbers there. And the origin of this enormous number is completely unclear. Okay, so that brings us to enigma of gravity. And by the way, as you see, this is a real enigma which existed in the world once. And to tackle this enigma was, of course, not an easy problem. And what we have here is, I think, is much harder. And this problem has one typical usual question, so which mechanism is actually behind the cosmological constant. But you can, using this relation between G Newton and lambda, you can invert it into the equation which actually mechanism is behind G Newton. And neither is known, at least to me. Okay, so let me remind you that calculating macromanager, we're actually in trouble because if you just sum up zero levels of all these oscillators and weakly interacting theory, we don't really know. There is no consensus how to calculate this quantity. And the only thing what we really insist on that the energy momentum tensor which appears out of this calculation should be proportional to G mu, because we assume local Lorentz invariance, and then that's the only thing we can write. So the point is that if we have, let's say, quantum field theory of massive particles, and we have a cutoff scale m, then people even disagree on the following: whether the proper estimate for this quantity is m to the 4, where m is the mass of the heaviest, let's say, particle, and then log of the ratio of this mass and cutoff, or it's just cutoff to the 4. And there is like big, actually kind of substantial literature on that. And another important thing is what is not even clear is the following, that in normal standard model, it would be almost practically scale invariant, but we have QCD scale and we have Higgs scale. But in reality, all the masses, if we go to really strict UV, beyond, let's say, electroweak phase transition, then all the masses of all particles would disappear. So in that sense, it's not even clear what to use in this estimation on the right. Another parameter would be neutrino masses, and that would bring us to the following points. That observations tell us that it's 10 minus 29 gram per centimeter cube, if you want to do it in mass energy density. And in particle physics units, it's 10 minus 3 eV to the 4. That's more or less neutrino mass scale. Then 10 minus 9 of electron, whatever, 10 minus 15 of energies, which we probe on LHC. So which is, of course, very strange, because we would like that such a parameter, if it's not technically natural, would just follow as cutoff power of 4. But as Pauli told us, that's not even wrong, okay? Because the universe would not be the size of moon, and that's completely implausible. So basically, we have no idea how to calculate it properly. And that poses a question whether the vacuum should really weigh or not. Okay, so now let me go to a more technical point. So there is a very old story, how to lose the trace, okay? And how to lose the trace in the context of Einstein equations. Namely, you take, instead of normal Einstein equation, so here I use normalization 8 pi g Newton is equal to 1. Of course, C is 1, and in most parts of this talk, h bar is 1. So instead of normal Einstein equations, you can subtract traces out of both objects and write just traceless part. So clearly, by doing that, you introduce order 1 modification to general relativity. It's a big deal. However, it turns out that Yankee identity plus energy momentum tensor conservation, which you have to assume in this setup, would imply that by applying to this traceless equations covariant derivative, you would see that the difference of traces of G minus T should be actually constant. And it's global constant, okay? Not just constant in time, but just global constant in whole space-time. After that, you can plug it in. And basically, if you denote it, let's say 4 lambda, that's what you will get. Okay, so that basically you are back to normal Einstein equations with some lambda. However, now this lambda is not, let's say, fundamental constant of nature or anything. It's just your integration constant. So it's some part of your initial data, if you want. So the interesting thing is that this was proposed by Einstein himself in this very nice paper, Spielen die Gravitationsfelder. Let me see what was written there, because I see myself there instead. Im Aufbau der materiellen Elementarteilchen eine wichtige Rolle. And for him, main motivation was that he disliked lambda to be a fundamental constant of nature. So he wanted that lambda is just less relevant object. And that's what he succeeded, and that's his paper actually from 1919, so it's more than 100 years old. Okay, so what is nice feature of these equations, because your lambda now is an arbitrary consequence of these equations. So if you look just at the trace of free equations, you immediately see that they invariant with respect to the shifts of T mu, which are vacuum shifts. So basically, you take whatever T mu you want, shifted by lambda G mu, you get exactly the same equation. You don't care. And it's clear why, because you have freedom to choose your integration constant in whatever way you want. Okay. And somehow, unfortunately, in the literature, it's known under the name unimodular gravity. And there is quite a substantial, basically, bulk of literature on that. So now let me just make a funny comment that, as you see on the right, we have D'Alembert, and on the left, we have Lagrange. And just let me remind you a simple mechanical fact that you could derive everything in mechanics just using high school equilibrium principle, that actually virtual work of all active forces should be equal to 0. And basically after that, you can say, oh, every motion is kind of equilibrium in the sense that they go in an inertial, non-inertial frame. Then I would get an additional force, which is minus ma. And therefore, in reality, what I should require is that this minus ma plus f, or if you want to invert the sign, multiplied by virtual motions, which I allow to virtual variations, would give me 0. Okay. And then if you add to this story the story about constraints, then you would get what is called Lagrange equation of the first kind. And basically the statement is that if the constraint has this variational form, then if you want, you can just think that the C is the gradient of the constraint. Then the force of this constraint, which is actually not an active force, but it is a force, is just what is staying, it's proportional to the real, basically, difference between this MA and F. So if you want, this is exactly the method of Lagrange multipliers, which just appears in this mechanical context. So, but now what you can do, you could use these basically equations to exclude lambda from there, and then they would take this kind of weird form, okay? So why am I mentioning this is the following, that you can take now normal Einstein equations, so J mu minus T mu, so they were normal. That would be equivalent of MA minus F. And now you multiply it with the virtual displacement or virtual motions of the now metric, so it would be delta J mu. And that should be equal to 0, but now you can put a constraint on your variations. So namely, it's a restricted variation, so that J mu multiplied with delta J mu is 0. So if you do that, then following this analogy, you get exactly what you wanted. So where instead of the small lambda, you get big lambda. Okay. So now, of course, you could exclude lambda by multiplying with J mu. And the story is that you will get these traceless Einstein equations. Okay. So on the other hand, you could use some other way to rewrite it. For example, you could multiply it with Einstein tensor itself, and by non-vanishing trace and inverse of the Einstein tensor, you could get very strange forms for the Einstein equations. And despite the strange forms, it's exactly the same so-called unimodular gravity or traceless Einstein equations, just different way of writing them. You know, they can be even more complicated, and they can even take the form that you make equality of only unit determinant parts, okay, of J mu minus T mu and the metric itself. So it's kind of also funny. That's the representation you would not find, but whatever. It actually gives you the same thing, all of them. It's just a question how you solve for this arbitrary lambda, for if you want for Lagrange multiplier. On the other hand, of course, we know that J mu delta J mu is just the point that you fix some function and you say that the square root of minus g is this function. And that's, you know, very often people just fix it, and then they fix it actually to be 1. And the interesting thing is that that's why it's called unimodular gravity, because you can achieve everything there by imposing a non-covariant constraint that square root of minus g is just always unity. Of course, the bad thing about that is that it's very anti-intuitive, because it would not allow you all normal coordinate frames, which are used in normal JR books. And these coordinate frames are actually built, as Landau-Lifshitz taught us, by material bodies and real clocks. So for example, in cosmology, we use proper synchronous time, which will be measured by guys sitting on each galaxy, right? And we use normal spherical coordinates. So there is no, which basically is the best suitable set of coordinates for the symmetry of our universe. And in most cases, if you try to do it in a unimodular way, you would not be able to do that. And that's, of course, a pretty strange requirement, even though, of course, it's a legitimate gauge, or it's a legitimate choice of coordinates, but then it's not clear why cannot you use normal coordinates for that. Okay, and then it was Noah Teitelboim who basically suggested to do the following. Let's actually make this F to be not in just some fixed external quantity, but an internal dynamical function, okay? And what they suggested is actually very interesting, because they suggested a theory for all de Sitter or anti-de Sitter spaces altogether, all of them. And this is a very funny system. suggested by them in 1989. Of course, you take normal Einstein-Hilbert action and you add this additional piece. This additional piece looks like an action with a constraint, okay? And interestingly enough, this constraint is not very standard, I would say, from the point of view of particle physics. So let's look at this construction in more details. So basically, if you vary these actions, then very easily you will get that mu nu is just lambda g mu nu. And clearly, if you vary this action with respect to W, which is one of your variables there, then you immediately obtain that mu lambda is equal to 0, okay? So that's exactly what we want. So this action, even though it's so simple, it has actually very interesting properties. So first of all, it has a gauge degeneracy with respect to shifts of this W by a vector which is divergentless in four-dimensional sense. It has a fake violation of the Lorentz symmetry, because clearly out of this constraint, so lambda is again a Lagrange multiplier, we see that the vector field W mu can never be actually 0. Of course, due to gauge redundancy, it's not unobservable per se, but nevertheless, it's kind of strange that we have some vector which should have non-vanishing VAF, maximum expectation value, but actually all our equations are locally Lorentz invariant, so there is no problem. So it's in a sense fake violation of Lorentz symmetry. Then, as you see, dark energy, or if you want cosmological constant, is a Lagrange multiplier. Okay, and this Lagrange multiplier makes equality between two different measures. So basically, if you write this divergence, you will see that you can rewrite it as equality between two different measures, which are there. This is already kind of funny situation. Another thing is that similarly to the Strugatsky Hamiltonian, this system is actually linear in canonical momentum. Okay, this is a bit harder to see, but you can think of it. Basically, I will show you in a second why it is so. Well, indeed, if you look so basically the only time derivative which is there is derivative of this VT component in whatever relation you choose. Well, if you follow that, then it's clear that pi is square root of minus g lambda, okay? And immediately you would know that because the system is linear in lambda, it's actually linear in your momentum. But interestingly, contrary to normal Strugatsky procedures, this system is not unstable, because this lambda is always constant and there is no way to abuse your opportunity to decrease your energy infinitely, because once you fix it on initial data, that's your result. Okay, so you see, very importantly, in a Strugatsky procedure, there is a loophole. So mu lambda is equal to 0. That's important. Okay, another thing is that this action is actually scale invariant, so there is no fixed scale in this action at all. Okay, so now what is more important is that if you look at, let's say, at this action using Fadeev-Jekiev procedure, you immediately recognize that as special derivatives acting on lambda are 0, they're just normal constraints which you can abuse in this action, then you can basically pass the integration over special coordinates beyond lambda. And in that case, you would see that the only degree of freedom which is canonically conjugated to lambda is this integral over time component of this field W. And you can compare it with the first order action, this normal, whatever, Hamiltonian action, PQ dot minus H, because this is very, very practically the same thing. Okay, so here what we will immediately see is that this gauge invariance generates just global shift symmetry of this coordinate. And you know, as we know from mechanics, if your system is invariant with respect to shifts of your coordinates, then you conserve momentum. So if you want, that's the verification why lambda is constant. So now you can look how this quantity WT integrated over Cauchy hypersurface, how does it change with time? And if you neglect on the boundary the values of this WI, then you would immediately see that basically the difference between these two coordinates is just 4 volume between these two Cauchy hypersurfaces. Okay, So, and again, shift symmetry in coordinate implies conservation of momentum. So, but now you see, it's a first thing. Surprisingly, I have not seen this trivial statement, even though the literature on unimodular gravity is pretty large. That because of this canonical, that these quantities lambda and the full volume between different hypersurfaces, Cauchy hypersurfaces, are canonically conjugated, unavoidably, you can apply the Heisenberg uncertainty relation. And if you restore all proper units, then what you will get is the quantum fluctuation of cosmological constant multiplied with quantum fluctuation of the volume, full volume, it actually should be larger or equal than 4 pi L Planck squared. And of course, for current universe, because, well, total full volume, who knows what it is, so, but if you want full volume between two hypersurfaces, it's still huge. But imagine you try to go to singularities, and singularities correspond to end of time, right? So therefore, you could choose, like similarly to normal hydrogen atom, you could choose the last point, it's where the volume is 0, and then you will kind of approach this point by squeezing this full volume, and that would imply that you would increase by quantum mechanics this lambda. Actually, I'm very curious to understand whether this mechanism would protect general relativity from creating this end of time singularities. And as far as we understand, all singularities in general relativity are actually end of time or beginning of time, if you want. Okay, so now let me proceed further. So this W mu is kind of rather unusual field, and what we thought with my student Pavel and another student Katrin, so whether it's possible to embed this story in kind of gauge system setup, let's say for some SUN connection. Okay, and then it was just a guess that instead of this W mu, one could use Chern-Simons current C mu for this basically gauge group. And if you do that, then you just really, you substitute instead of W, C mu, but then you know that nabla mu, C mu is this FF dual. And it can be abelian, non-abelian, doesn't matter. So now let's look at it. So this is Chern-Simons current for a non-abelian gauge system. And the good thing for us is that this CT does not actually depend on DT mu. Okay. And this is the key property of that, because as you remember, the real observable was there, the integral over this CT. In reality, even the difference between different integrals. But what we care is the integral over CT here. And therefore, in this substitution, we don't change the proper structure, if you want symplectic structure, because we don't substitute DT mu in a proper, so to say, invariant dynamical part of the story. So therefore, it's a legitimate substitution, but it's non-trivial one. Okay, so basically, that's what you get usually for Chern-Simons. So you can see at gauge transformations, these gauge transformations will actually introduce shift of this Chern-Simons current, and the shifts which are proper, which are actually divergentless. So now let me go a bit in historical context. So basically, I have not seen discussion of this formulation of unimodular gravity anywhere in the literature. If you have, like, let me know. But what was very close to that, as I discovered, there was a paper by David Finkelstein, and that's the guy from Eddington-Finkelstein coordinates, even though in the way which we use it now, it was only written in the paper by Penrose, for which he got Nobel Prize. So what he was saying about this unimodular gravity was pretty interesting, because he was saying that cosmological constant may be related to some fundamental lengths, and that this ambiguity is kind of, you see, so lambda appears as a Lagrange multiplier. And then he was saying that the fundamental scale of lengths in atomic physics provides such a hypervolume element. So, and of course, in reality, if you think our FF dual, if you forget about, let's say, you go to proper Pontryagin density, you kill the square root of minus g by which you divide it, then it is kind of hypervolume element coming from some non-abelian Young-Mills system. And so you see, that gave us a sort of a speculation that, it's kind of weird that we talk about cosmological constant, but in reality, we have a system which is QCD, even our QCD. And it's actually IR strongly coupled because it's confined. So basically, it's kind of very weird. So we use in cosmology, we kind of forget about this strongly coupled vacuum of QCD. But in reality, it is there. So who knows, maybe it's even causing us to have a cosmological constant. So now from this action, another historical remark is that Frank Wilczek was speculating in '84 that it would be great to do the same procedure which he has done for theta parameter by introducing the axion to cosmological constant. But if you look at this paper, he doesn't provide much details, but here we are already very close. Okay, and now let me tell you, almost normal axiom. Okay, let's start from an action which looks like Einstein-Hilbert action. And then I write an axionic coupling of some axionic field theta with this FF dual. So now instead of tilde, I use star. And then, I write instead of just theta there, I will write a general function of theta. Okay, so it's clear that for us, what was important that this that this gauge field A had FF dual but did not have F squared. Okay, and because of that, theta will be constant, and that enforces you on shell that this theta squared, the basically kinetic term for this axion, is 0. And therefore, this potential is just an arbitrary function, basically an arbitrary number, because theta is always constant. Okay. Just for completeness of notation, this chi there is 8 pi j Newton, just takes too much space. Okay, so now we could add proper kinetic term for the gauge field, and I'm using this non-canonical normalization. And you would see that actually you can get the action which I was talking about just from formal limits. So if you take coupling constant going to infinity, then you obtain what we want. Of course, it's a bit strange, but the thing is that if you do proper canonical normalization, then this g squared would appear in front, not dividing but multiplying the FF dual part, and therefore in this limit you would have the huge theta term if you want. So for me, it's pretty interesting. I don't know how to think about this formal limit and whether it has anything to do with confinement. However, kind of naively, if we don't kill kinetic term for the gauge field in some quasi-classical approximation, which is of course the wrong word, but I don't know how to properly think about it. But it's kind of an attempt to go a very quantum regime and try still to use some classical analogy. So, but if it is true that we could kill this term, then that would give us what we want. And that's one of the central things what we abused in this paper. Okay, so basically this kinetic term is irrelevant. Okay, now let me go to another side comment that actually Tony Padilla and Jan Kimpton turned out. So Tony mentioned me during one of my talks. I was not aware of this work. So they were doing following things. So they would say that suppose that somehow all fields are connected not to normal metric, but to some composite metric. And this composite metric is multiplied with total derivative in such a way that everything what will be generated through loops would be, of course, proportional to this square root of minus g integral. But if this g is composite and in front is a total derivative, then it's irrelevant. Okay, so it's basically, it's a very, very different way of thoughts. And importantly, that he was stressing that it's not unimodular gravity, but actually we found that it is. It's nothing else. Okay, so now let me go to the second way of losing the trace. And basically what I'm telling you is that one can do it 1-1 instead of 0-0. So namely, before that, we were taking the trace out of our equations so that they were basically trivial identity was 0 equals 0, because it was g mu minus 1/4 metric multiplied with trace, and the same for the energy momentum tensor. And here it's a trivial identity, 1 is equal 1. Okay, so that's a funny equation. If you want to memorize something out of this talk, which would be very, very easy on equation level, this is the equation you can memorize. The funny thing is that's again Bianchi identity and non-degeneracy of T mu. Suppose, for example, it takes small lambda itself, right? Would imply that in the same way as you do for traceless equations, that now it's the derivative of log of g divided by t is equal to 0. And that implies that t is just proportional to g, where t and g are traces, okay? So therefore, what you obtain M Planck, or if you want G Newton. Here, I think it's more proper to say it's G Newton with some coefficient. I always forget what was the power of the speed of light there. So, but basically it's 8 pi G Newton, which becomes your integration constant. Okay. So surprisingly, I have never seen such a simple equation discussed before. So basically now you promote G Newton to a mere integration constant. So importantly, it's not like in Brans-Dicke where it's a proper field, but here it's just constant global everywhere, similarly to lambda. Okay, and now we can again abuse this D'Alembert principle in constraint variations. And it's very funny because you can impose constraints that T mu multiplied with delta G mu should be equal to 0. That's what we called energy transverse, contrary to normal transverse gravitons. And that would give you immediately the same thing as you see. So J mu minus T mu is proportional to lambda T mu. But this lambda now it's a field. If you work out Bianchi identities and so on, you get the same story that you need to have it constant. So, but of course there are other ways to do it. You can solve it with, solve with respect to lambda, write it in the way which doesn't have lambda. Importantly, these equations are scale free. So there is no scale there at all. Okay, another side remark is that you could do what we call Einstein transfers. And because you see in these equations, they're more or less symmetric. So you can say that your variations of the metric, or the contravariant metric, are restricted so that if they're multiplied with Einstein terms, they're 0. If you impose these constraints, then you get again the same equation in the same way. Okay, so basically now what we have unitrace or scale-free Einstein equations, and using different ways of rewriting them, you can even write them as unideterminate equations. Still the same thing, no difference. Okay, so now then we thought how to get them out of the action. And the simplest way is to do this in Otto-Teitelbaum analogy. So basically you use again some vector field, and you use Lagrange multiplier, and then easily you see again by varying this action with respect to C, you would get that alpha is a constant. And itself, this nabla mu C mu multiplied with alpha does not contribute to any gravitational equations at all, similarly to the point with W. So you can compare, so this is very simple, but you can compare it what Nemanja Kaloper, Tony Padilla, and George Zachariade with, I think, Paul Stefanishin, I have forgotten his name, what they were doing for sequestering. But here I should admit, I don't properly understand this vacuum sequestering story, so I would be happy to discuss it. But they use much kind of more complicated formulation. Okay, so now, however, what do we see is that in this way, similarly to this unimodular story, you have alpha, which is roughly speaking M Planck squared, and now there is this quantity which is integral of this CT, and it's canonically conjugated to this alpha. The same thing, it's kind of, if you want, it's kind of charge which constantly gets produced, and the production rate is, so the source is your Ricci scalar, okay? So basically the quantity which is now conjugated to M Planck squared is actually integrated Ricci scalar. Okay, and that's what we called Einstein transverse way. Basically, that's similar to imposing, but not identical, to imposing these conditions that actually this G mu nu, delta G mu nu is equal to 0, where G mu nu is the Einstein tensor. Okay, so now the point is, if you have conjugated quantities, they can immediately write Heisenberg uncertainty relation. So the best way to write it is actually to use L Planck here instead of, so the Planck length instead of Planck mass. And then it takes this pretty elegant form. So basically the quantum fluctuation of Planck length divided on Planck length itself, you multiply with the fluctuation between two Cauchy hypersurfaces of integrated Ricci scalar divided by, again, Planck scale squared, and that's larger or equal than 4 pi. Of course, now for current universe is completely irrelevant, but for quantum cosmology, that would definitely have consequences. And now we can go to, again, the same axionic picture. Basically, using this analogy, I can write instead of this C, I can write some Chern-Simons current. And if I do that, by the way, there are 2 pluses instead of 1, sorry about that. So if I do that, then I get non-minimally coupled system, which looks like an axion coupled to R through nu squared. And it has a potential. So if you want, I can simultaneously gain also a cosmological constant if I want, but I could take this potential to be 0. And again, I'm taking this formal limit that the coupling constant goes to infinity to kill the normal kinetic term for the gauge field. Okay, so now I want to tell you something even more kind of unusual. So namely, you see there were 2 ways, right? 2 different conditions. So either Einstein tensor multiplied with the variations of the contravariant metric was 0, or energy momentum tensor multiplied with the variations of delta G of contravariant metric is 0. So we looked at what is the, so to say, Einstein way, but now you can write actually a meta-transverse way, okay? Just by recalling the following things, that if you have a constant in front of your Lagrangian for matter, then effectively your G Newton will be different for coupling to matter, right? And of course, if you just write normal general relativity without any matter and without cosmological constant, why would it care about G Newton at all? So basically now what we suggest is this funny action. So you have beta as your, again, Lagrange multiplier, but now this Lagrange multiplier enforces you that the total matter Lagrangian density should be equal to some 4 divergence of some vector field, which is again a dynamical quantity. And you see, the funny thing is, so if you proceed in this way, then you look at normal canonical momentum, right? Defined as usual through the, well, now you have total Lagrangian density. And that will be rescaled by beta with respect to the one, to the canonical momentum, which you get just thinking about lambda m. So basically thinking about Lagrangian m, this curly Lm, you get, of course, different canonical momentum, right? But here, the proper canonical momentum is rescaled. So that implies that if you look at canonical commutation relations for, let's say, field phi and its canonically conjugated momentum, which you just obtained through Lagrangian density, then they get rescaled. So it's not IH bar anymore, but it's IH bar divided by beta. And that implies that your effective H bar, so H bar bar, if you want bar bar, is equal to H bar divided by this beta. So that sounds a bit strange, but if you think about it in terms of normal gravity, then clearly canonical commutation relations for normal, let's say, fluctuations of special metric and fluctuations of, let's say, extrinsic curvature, which are corresponding to the canonical momentum conjugated to it, they do care about G Newton. So basically, they do care about the whole coefficient in front of whole action. And therefore, if for fluctuations which are canonically normalized, so for normal, let's say, H's, right, it's all fine, then for fluctuations of the metric, you will know about the coefficient in front. You will know about G Newton. Okay, so now what you can immediately do in that case, you could imply Heisenberg uncertainty relation, right? Because now you know that this beta from this formula is canonically conjugated to minus integral of this vector field L. It's T component. It's direct analogy with not Teitelbaum. Then the difference between these different T's is just again this LM integrated over there. So therefore, what you see that the fluctuation in this H bar bar, if you want, is restricted. So you multiply it with also the fluctuation of this object, and this object is nothing else, is actually action, right? It's an action between two hypersurfaces of whole meta sector, and it can have fluctuations, right? And it should be larger or equal than 1/2 H bar bar squared. So it's a pretty funny uncertainty relation on even this effective H bar. Okay, and now you can of course do the same procedure by writing its almost normal axiom. So basically, let's take normal Einstein-Hilbert action, and then augment it with some new axionic light field eta. And so this eta, what is non-trivial, that we wanted to couple to the whole Lagrangian density of whole meta sector. You can introduce then some mass scale if you want to write it properly. So this is just formula for canonical normalization. And then again, it's some other gauge field. Again, you use the same thought for this. Of course, if you have potential for the story, then not only you change G Newton and H bar, you also introduce some cosmological constant by doing that, because eta on all equations of motion is going to be constant. Okay, so finally, I think I have like 10 minutes. Am I, Mitya?
Yes, 10 minutes.
Yeah. So I'm practically done. But now I want to tell you something kind of funny, that many people would write unimodular gravity as just Einstein-Hilbert action, this addition of this term above, so which is just non-canonic, non-covariant term. So Lagrange multiplier enforcing that square root of minus G is 1. Okay. So many people would think that this is exactly the unimodular gravity, and people would even try to quantize it and do whatever. So interestingly enough, there are also many claims in the literature which are completely erroneous, that this thing does not do anything because it's just a gauge. It's a gauge choice. But now, if you recall about how the properly covariant unimodular gravity is constructed by Teitelbaum, then we know that even to write this action in this form and this non-covariant form would require from us to fix W. For example, one can fix it as it's written here on the right. And that implies that you don't have any more this freedom to choose the gauge. You have already fixed diffs for your time coordinates. And therefore, actually, this constraint is not just purely choice of gauge. It actually contains dynamics, because in order to write it in this way, you have already to choose a gauge to be allowed to do it before. Okay, so that's what is kind of important. The good thing about this W is that by shifting it by this epsilon, you can always choose it to be time-like with this coefficient. So there is always, in the paper we have a simple proof, but actually it's known before us. So in reality, when people say that this unimodular gravity is just mere constraint, mere gauge choice, it's not true, because when you have to write it, you have to choose the gauge beforehand. Okay, following now this analogy, you could choose this other vector field, let's say C or big L, and then you could write unimeta action. Okay, that sounds bizarre because it's also not generally covariant. So it will have this beta square root of minus g, total Lagrangian density, -1. Of course, also it's clear that it's a bit odd because for normal solutions, in normal field theory, for free fields, in most cases, Lagrangian density is just 0. So what you can think that, okay, let's say in electrodynamics, it's 0, right? But you can think that you add a small cosmological constant there in matter sector, and therefore this LM is never 0, then it's a mere gauge choice, again, formally speaking. But in reality, you know, you work out all equations of motion and so on, and you will get the same story of what was this, so to say, energy transfer story when you get M Planck to be constant of integration. So basically, through Bianchi identities, this beta would be enforced to be constant. And that's very important, and that's non-trivial because T mu, which is written now because you have already, in some sense, broken diffs. So T mu is actually not conserved, but it's not conserved in such a particular way that Bianchi identity, which is still satisfied, would force beta to be constant. So it's a bit non-trivial. So I omitted it from the presentation because it takes a bit of time to show. But in the paper you can find it. And more simple option, you can put this constraint now on curvature itself, and you can write, instead of unimodular gravity or unimeta gravity, you can write unicurvature gravity. So again, formally, it's a gauge choice because I can always choose my gauge element to be equal to 1 divided by r, provided that I have some small cosmological constant. Then basically I would omit solutions of complete measure 0 because I would need them to stabilize them, and that's impossible, right? So one can check that this action, which is again non-covariant and looks bizarre, through Bianchi identity reproduces what we need. So namely, it would reproduce you just points that the G Newton is a constant of integration. Okay, so I think by that I'm done, and I think I have even 5 minutes time, but you know, I planned for many questions and I hope they will come, and thanks a lot for your attention.
Thank you. Are there any questions?
I think there are 6, if you look. I think the 6 chat.
Chat messages.
6 chats. Okay.
That was something like technical.
Yeah,
stuff.
but they're not real big questions.
So can you return like to those
I'm
slides where
surprised.
you explained about uncertainty principle for this kind of fundamental constants? So you had, let's say, cosmological constant, and what was like the dual thing to it? And I'm wondering how you understand how you understand this formula. So this is like all kind of global parameters, right? So lambda is.
So that was the first one. Let me do the thing.
Or we can go to
so
the
that was the
second
first. Yeah. So basically, this one is the most standard one. So basically, all people who do unimodular gravity, they should have this uncertainty relation. But why it is so? Because if you look at the structure of this action, you can compare it with the PQ dot minus H, right? And think that special derivatives acting on lambda, that's just a mere constraint thing because it doesn't involve any time derivatives. So in the first order Hamiltonian formalism, this thing is your constraint. So therefore, you can use this constraint in this section to see what your symplectic structure. But then it's very easy because this is lambda, and then you have the time derivative of this VT. But there is also three-dimensional integral, so therefore that's what you get. So basically, you get this quantity, which is sometimes called actually from the cosmological time even, but it's not proper cosmological time in normal sense. So the thing is then, because this is your coordinate, but there is shift symmetry in this coordinate, what makes sense, it's only to fix some origin, right, in such a coordinate, or it subtract one of the value from another pivot value. And then you see that the difference between these two coordinates is just your four volume of the space-time. But between two hypersurfaces. If you look, by the way, in the discussion by people who were doing sequestry, they constantly talk about global objects, including kind of future boundary conditions and things like that. Here, it's not needed. You can always say that I choose something in the past, and then every time I go forwards in time, I just subtract this value from the past one. Of course, you can also do a bit weird procedure, and you can say that, okay, I kind of suspect what is going to be in the future, and I subtract this value from the future, because this is just the equation of making constant subtraction. So this was the simplest
so apply to our
relation,
universe.
but I think you see what happens. Imagine,
like apply to our universe. What would this mean? So it just gives a limit on.
Can you repeat it, please? Because
apply
that was broken connection.
Can you hear me?
Yeah.
So I'm wondering
whether,
like, apply to our universe, what does it mean? So does it give a kind of lower bound on for volume?
Good question, because you see, what one could do is the following. Suppose our universe is closed. Okay. Of course, then from inflation, that sounds that then it should be closed on enormous scales, like really, really enormous scales. In that case, I can really calculate what is the full volume between two slices in this closed universe. Okay. Mm-hmm. And then I would know that if I take them very, very close to each other, then of course the difference would become kind of zero. And that would imply that if you want on time scale, which is the difference between these two slices multiplied with three-dimensional, let's say, difference in three-dimensional volume, I should have this fluctuation of lambda. So in some sense, it's kind of almost like energy time uncertainty relation, which is usually not a good relation in quantum physics. But if one understands it in a particular way, let's say Tom Mandelstam, then one can understand it. So I think what is really relevant there, because you see clearly three-dimensional volume in our current closed universe would be enormous. And then the difference in times, which you need to make any sense of this lambda, would be really, really tiny. But formally speaking, of course, that introduces some limit on time, which does not create bigger fluctuation of lambda. So for example, we could take current lambda and say what is the minimal time span which we could get in order not to see the fluctuation of this lambda larger than the current lambda. But I bet you that should be like really, really tiny. And of course, on top of that, we don't know what it is exactly, because we don't know the whole size of this closed universe. So the story actually gets more complicated on formal level if we start working with boundaries. And that's actually, I don't know yet how to understand, because this whole story was without boundaries, without boundary terms and so on. But part of this information about lambda and conjugated quantities should actually reside on boundaries. But that's not done, and it's not even clear for unimodular gravity yet. So now, if you go to the same construction, but let's say for these other guys, I mean, like for this L. Planck, you could think about this as written there G Newton, but it's more or less the same story. You write because L. Planck is square root of G Newton, it's some h bar, right? So you would know also that if you have some curvature which is there, you make this squeezing, again, two small differences between hypersurfaces, and then there is G Newton which is fluctuating strong enough. But most probably it's much smaller, than L. Planck, on which it already doesn't make a lot of sense, I would say. But interestingly enough, it's global quantities. They don't care about your, you could write all possible higher order terms for gravity. Let's say you work in effective action for gravity, you could write the cubic terms or whatever, and nothing will change in this picture. So that's important. So this picture is ambivalent for that. And here it's a bit more bizarre. So, but basically it's an action of whole matter sector between two slices. You take extremely small value of your time between the slices, and then you would see that, well, this thing, if it fluctuates as it is, then this product should be larger than that. So that's basically your effective H bar would be different from what you would think.
By the way, how you understand?
So that's.
Sorry, I want.
Oh, look, it's from this. Yeah. No, it's very good. So look, that's a very simple statement. So suppose you don't know about this construction with this Lagrange multiplier beta at all. So just think about that. That's your standard Lagrangian, let's say, for whole standard model. Okay. Then in this real action, in the proper one with beta, you know that your canonical momentum is not what you used to have. You just multiply it with this beta. Think in terms of normal gravity, right? In normal gravity, without matter, nobody would care about G Newton. If there is no matter, no lambda, nothing. Just the G Newton, you can forget. Everywhere except of when you quantize it. Because immediately when you quantize it, you know that you need to satisfy this uncertainty relations and so on. And in this uncertainty relations, this G Newton would pop out. And here it's the same thing, just this beta is a dimensionless field, it's just a rescaling field if you want. And if you just follow your standard canonical momentum, then suddenly you would see that what you have there is not H bar, but this H bar divided by beta. In kind of straight way.
Okay, I see.
I have a question. I suppose you have a chaotic inflation, which is completely different. Okay.
Mm-hmm.
And I wonder, and chaotic inflation continues because the scalar field, it has fluctuations, and therefore it causes the lambda, effective lambda, to fluctuate, and inside some finite volume, right? So my question is whether your kind of simple uncertainty relation is valid in that case as well. I mean, if you multiply the for volume of fluctuation times a fluctuation of the cosmology of the scalar field potential, right? In whether this product also satisfies this inequality.
Good question. You know, I'm not sure because you see, the point is for chaotic inflation, we would need to restrict this Cauchy hypersurface because you see here it's for total Cauchy hypersurface. So if we have, and in chaotic inflation, we don't even know what's the global structure of the whole story, right?
Yeah,
so,
yeah, it's completely different, and the effective lambda, it fluctuates in a finite volume, in finite volume, of course. But I wonder just whether your uncertainty relation is valid in that case as well, which is just a practical question. Okay.
Formally speaking, it should be valid. Whatever you give me, Cauchy, like basically you give me a set of foliation of space-time, then it will be valid, because if you believe to this first formula, basically. But what does it mean? Because you see, it's kind of weird. If you take whole Cauchy hypersurface in eternal inflation, then I think it's enormously large, right? It's like
no. I mean, if you take not a whole hypersurface, but a part of it,
Yeah, but you see, that's exactly the point, because look, for example, at this formula, let's say
Yeah,
here.
but I'm not talking, Alex, I'm not talking about the unimodular gravity anymore. I just wonder whether the same uncertainty relation is valid in different models.
Oh, you mean not in the setup we're discussing now, but just in more general case?
In more general case, in chaotic inflation, for example, or
Good,
in
good question, because you see, but there formally we kind of know what it is, right? Because we know what are our quantum fluctuations
yeah,
in reality of the scalar field phi.
yeah,
It's a normal canonical scalar field, and there you would definitely know basically how on very large scales these fluctuations look like. And of course, they would satisfy uncertainty relation, but even much worse, right? Because what you would have like delta phi, let's say, multiplied with canonically conjugated delta phi dot. Probably there would be some measure factor depending on which coordinates you use to parameterize your fields.
yeah.
And then after that, it would be the equation on which scale you average your fields. So basically how you filtered them. And this scale would be, I think, like pretty enormous, right? Because in normal inflation, it's very easy to estimate. You just take whole basically size of the curvature, and then delta phi averaged on scale of curvature, delta phi dot averaged on scale of curvature. It's nothing else is larger than h cubed, basically, right? Where h is Hubble. After that, you can even get standard estimations that delta phi is, roughly speaking, Hubble. If you assume that the time derivative, the delta phi dot, is estimated as delta phi multiplied with h, because that's your frequency now. And in that case, a normal kind of inflationary setup on scales of horizon, you just, in a sense, saturate this uncertainty relation, because there you're kind of almost in vacuum. If you go to larger scales, of course, there you don't saturate it. You have fluctuations which are much larger actually than uncertainty relation, because there you have particles, and basically it's like the equation in an oscillator. You go to highly occupied level, and in highly occupied level, actually this, let's say, delta Q delta P is not h bar half. It's like this factor, I think, square root of n. Sorry, it's just n. Sorry, just n, where n is your occupation number. So it's much larger. And in inflation, if you go to scales outside of curvature scale, then your occupation numbers are very quickly getting like completely crazy, like 10 power, I have even forgotten, 60, 50. So this all will be huge in that sense. And especially in eternal inflation, where the fluctuations are so strong that they're larger than classical dynamics. So in that sense, it's a good question, because there, it's easier. It's not a global dynamics. You just need to average properly on some Cauchy hypersurface and some volume, and then look what will happen there. Okay. But you kind of know that on these scales you can forget about uncertainty relation, because the product of your fluctuation is much bigger, like exponentially bigger.
Okay, thanks.
Okay, I would like to ask a question, or maybe make a short remark. As far as I can understand, please correct me if I misunderstand you. You see these nice uncertainty relations by considering a symplectic term in the action which involves your auxiliary fields. So you see that the variable which plays the role of cosmological constant in the first story of losing the trace, and the role of Newton constant in the second traceless story. It has a conjugate which is space-time volume or something like this. And you see it by looking at the symplectic term. Am I right? Do I understand you correctly?
Absolutely, absolutely.
Yeah, very good. Actually, I have some doubts about equivalence of the action you construct with this auxiliary fields and your original nice idea about the second way of losing the trace. And let me say that these equations by construction are not Lagrangian, but this does not mean they are not Hamiltonian. There are examples, in particular in our works, where we constructed for higher derivative non-Lagrangian equations, Hamiltonian formulations. They are still Hamiltonian in the first order formalism, and they can be quantized, even though the vertices are non-Lagrangian. And I think that the same story is correct with at least Einstein's way to lose the trace. So you don't need, in fact, the trick of a not Teitelbaum to find the conjugate variable to, in fact, scalar curvature, because your cosmological constant as a function of metric, it's just scalar curvature, which is not zero, but integration constant on shell. So it has probably conjugate variable in a sense. I don't know in which sense, but if you look at our works, there is a technology to equip such equations with Hamiltonian formalism without introducing any auxiliary fields. That was a remark.
Right, right. But you see here, it's actually very easy to see the structure of the story, because, you know, in not Teitelbaum, they were doing actually the opposite job, right? They thought that this unimodular classical story that square root of minus g is 1, it's insane from a very simple perspective, that it's very weird, right, to impose such a constraint on coordinates you use. And they wanted to covariantize it. And basically, they have done an inverted procedure. They started from this strange unimodular structure, and then they covariantize it. And after that, you can see what are your degrees of freedom. So what is hidden there in the structure. So in that sense,
excuse me, I'm not completely, I understand what you mean because I worked in this field and I understand what you mean, but I don't completely agree with this comment. In fact, in unimodular gravity, you don't have the general covariance at the level of gauge symmetry. You have only volume preserving diffeomorphisms. And they just try to introduce, if you wish, Stuckelberg field to make to restore the complete general covariance. And it's also not completely convincing, but basically for me it's okay that they did it. And
by the way, you are absolutely right, because this kind of vector field is a Stuckelberg in some sense. But you see, the interesting story is the following. So let me go to the last slide. So in reality, how you can get the unimodular gravity in which you break different variants. So the one which is given by this action, right? You just take a Teitelbaum and put this and that there. So you see, you use really the Stuckelberg freedom in some sense to make this W to be Z. And if you do this, then you obtain unimodular gravity. It's true. But you see, the original story is, so they're not original, but the story of a Teitelbaum, at the end, this action, I mean, if you take this action, let me show you this slide. This one on top, there is no doubt that it's generally covariant, right? It's just, it is what it is.
Yeah, it is explicitly covariant, of course.
Exactly. And that's actually an interesting story, because, of course, Simens, you're absolutely right. There are some interesting kind of original thoughts behind what would be called unimodularity or transversality condition, exactly as you said. That, for example, if you work on the level of a little group for gravitons, then you don't obtain as a requirement the full different variance. You obtain only this transversality condition, actually. That's so basically, if you want to reproduce gravity theory from normal linear Lagrangian for spin 2 massless particles, then you don't obtain GR, strictly speaking. You obtain unimodular gravity. And that's this old work by, I think, Stephen Xu and Jack and G or something like that. So at least they were, for me, those guys who the first wrote it. And it is very, very interesting from that perspective, right? That just kind of formally speaking, normal particle physics algorithm, how to write an action for this interaction field, doesn't produce a jar. It produces this unimodular stuff.
Actually, there was a work by
sorry, just a
by
moment.
Glass,
Sorry.
Alvarez and others who did what you are speaking about, spin 2 pure irreducible representation, and it is in fact linearization of unimodular gravity, not jar.
By the way, which work do you mean, Simon?
It was work by Alvarez, Blas, and some others who
By Diego.
they proposed true irreducible spin 2 theory, which realizes without any auxiliary fields the irreducible representation of massless spin 2, and it corresponds to linearization of unimodular gravity, not jar. This is known fact, I agree, but the authors are different.
Sure. No, but you see, Diego and company, they wrote it much later, because the paper I'm talking about, let me open.
Oh, I did not know.
Yeah. Let me tell you what is the, just a sec. So I need to open the proper thing.
Sorry, as it goes over time considerably, let me just formally announce the end of the seminar so that people can go if they want. And you are free to discuss, of course.